Welcome back. We're gonna resume. We're gonna pick up from yesterday, second.
So actually, before we get to the proof of the Kahn-Kalai conjecture, which we ended staying yesterday, let me briefly introduce you to, I guess, a quite distinct place where the same first moment obstructions come up, and we'll very soon see how it's closely related, goes in parallel with the Kahn-Kalai conjecture and the story of threshold, and it also will give us crucial insights. So let me quickly switch gears and tell you a little bit about Talagrand selector process conjecture. And to keep the discussion friendly, I will actually state it in the combinatorial form. So Talagrand was not motivated by the combinatorial application. He was working on questions related to suprema of stochastic processes, and he posed this conjecture in that context, which I will only very briefly tell you about how that comes up later. But he already realized that this question can be reformulated in a combinatorial form, quite closely related to the Kahn-Kalai conjecture. And he actually posed the fractional Kahn-Kalai conjecture, so that's another conjecture of Talagrand in the same context. So there is a very beautiful word in probability theory that Talagrand painted, which I would try to tell you just a little bit, and hopefully I can convince you that that word is itself very rich, and it tells us a lot about the different facets of the phenomena that we may observe when we talk about threshold. Well, first, let me just give you the statement of the conjecture. So the setup would be very close to the setup for the Kahn-Kalai conjecture, at least in the form that I'm going to state it. So we will have some family of subsets of an arbitrary finite domain X, and the only assumption is the same assumption that comes up in the Kahn-Kalai conjecture. So we have a family of sets, which is not piecemeal. And now what will be given to us will be the following information. So for each of the sets in our family script H, someone comes and gives us an arbitrary weight vector. You can think that someone comes and gives us an arbitrary distribution or valuation of the elements of the set H. So we are given this weight vector of valuation or coefficient, however you think about it. And it takes the elements of H to some non-negative weight. Okay, so we are also, let's assume for normalization purpose that the sum of the weights over all of the elements in H is, well, let's say at least 1. You can also make it equal to 1. Right? So if you write this down, then in other words, someone just comes in and gives you a distribution over the elements in H. It doesn't have to be the uniform distribution. It could be, in fact, an arbitrary distribution. So we can just arbitrarily divine this weight of 1 across the elements of the set H. And the conclusion is that if we now look at the following quantity, so we'll have some random variable, we'll look at its expected value of the random variable. We will maximize over the sets in the family script H. And what we try to maximize is the following quantity. So remember that in the setup of the Kahn-Kalai conjecture, we have a random subset of the domain where each element is sampled independently with probability P. The same set will appear here. And this is the quantity that we care about. And the claim is that there exists a universal constant such that this statement holds no matter what finite set and family of subsets H you are given, and no matter how this weight lambda H is chosen. Okay. So just because we first see it, let's maybe see it in the one simple case to clarify what this means, at least in the simple case. So for example, we can take, so let me write down this corollary and see how we get it. So let's let H be a collection of sets of size L, which is not P small. Then the conclusion is that if we sample a random subset, XP, so note that, well, so far in this discussion, there's never been any log factor that appeared, right? So we assume that the family is not P small, and the random set has always been sampled at the same density P. We don't have this log L that we have in the Kahn-Kalai conjecture. So here what we get is that or let me write it actually in this form. Then with probability at least 1/2. A random subset XP, there would exist a set H from the family such that XP captures at least some constant fraction of that set H. Okay, so for the Kahn-Kalai conjecture, the statement that we had was that if we sample not the random set at density P, but density roughly a constant times P times log L, then the claim was that we can guarantee that there always exists, with reasonable probability, there would exist some set H from the family for which we can capture entirely that set H. So that would be L on this right hand side. So we know that the log factor there is necessary, but what we can guarantee when we don't have the log factor, when we don't blow up the density by a log, is that we can always capture at least a constant fraction of some set from the family. And this would just follow very quickly as the easy special case of the conjecture if we just take lambda H of X to be 1/L for all of the elements X in H. So we just uniformly divide the weight across the elements in the set H. And we will see roughly that the selector process conjecture and questions around it in general are some kind of weighted generalization of the Kahn-Kalai conjecture, where if we specialize to uniform weights, then we can appropriately work back to get the Kahn-Kalai conjecture. This one may be the quick comment that I want to make, which is that this corollary, we will see soon later, is very closely related to the main lemma in the proof of the Kahn-Kalai conjecture. That's the main point that I will tell you about in the later half of today. And in a sense, you can imagine the following intuitive but not quite correct process. Well, you take one single sample of a random subset of X, it can capture at least some constant fraction of a set from the family script H. If you can somehow iterate this process, you can take new samples, and if your new samples keep being able to get at least a constant fraction of the sets that you have been able to make progress on before, then you can believe that in some soft way, after logarithmically many iterations, you can fully capture one of the sets from the family script H. This is not quite correct. It doesn't work under just this corollary, but we'll see that is a very simple strengthening of the corollary that will allow the iteration to go through, and that's exactly the proof of the Kahn-Kalai conjecture that you will see. Okay, so I will just, maybe since I mentioned the context, tell you a little bit, at least about where this conjecture connects to in probability theory. So that's at least the original birthplace of this question. So it turns out that it connects to, so first, the one connection that's already obvious from its form. It's kind of a very interesting statement about the behavior of a linear program, or in other words, some optimization problem under randomness. So in other words, let's look at this function right here. All that we are trying to do is to optimize over this kind of random variable or this kind of function right here. And what is this function? Well, if we think about xp as being given by its indicator vector, then this is just simply a linear function of that indicator vector of xp. So in other words, you can think about this as of a linear program and how it behaves under a random sparsification of the domain. But the main connection is that it comes up in the study of Suprema of an important class of stochastic processes, but for this one specifically, it's a positive selector processes. So I will not tell you a lot about the details of this, but just briefly for context. So a selector process is a stochastic process. It's given by the following information. You have a collection lambda of weight vectors, exactly like these guys. So these are just a collection of weight vectors lambda that assign some non-negative weight to each element of the domain X. And now you consider the following information. So given a subset Y in X, we can consider a random process driven by the randomness given by the subset Y, where at lambda, the process just evaluates to, well, the sum over the elements in Y the weight given by lambda on that element. Okay, and usual, well, it's a suprema of a process. So what we are interested in is this type of random variable that is just the maximum over these random variables, C lambda. So it turns out that in this language, in this context, that conjecture has an equivalent form. And this was how Talagrand posed it originally, really around the same time as the Kahn-Kalai conjecture. So he conjectures that if we look at the tail event of this random variable, so if we look at the event where the suprema of the process exceeds its expectation by some large constant factor, well, just by Markov inequality, we know that this is a tail event in the sense that it has a small probability. But what's important for Talagrand is that this event is not just an arbitrary event with a small probability. It actually is an event that is small in a very explicit characterizable way. And in particular, he conjectures that this event is p-small. So in this language, he's using the first moment obstructions as a way of characterizing the additional nice property of some tail event, or some small event. So roughly being p-small means you are not just small, but you are certifiably small by the union of these very simple offsets or half spaces, if you want to think about it in another way. And it's kind of, this is just for context, this is how this conjecture comes about. Quite easy to actually connect them, but I won't show you the details. And yeah, so it turns out that one of the motivations for this was that an analogous result is proven earlier by Talagrand for Gaussian processes. And a similar conjecture is made for an even wider class of stochastic processes, so for positive empirical processes. And empirical processes actually appears in quite a lot of places, and they're quite general. So, okay, so with that, on the probability side, I'll just stop here. I'll just mention that the selector process conjecture in the form stated over there or here, and the corresponding questions for empirical processes. So these were both proven in my work with Jin Young Park, also just appeared this year. And in fact, this work, even though the argument is quite a lot harder than what goes on that you will soon see in the proof of the Kahn-Kalai conjecture, is actually the original source and the motivation for the Kahn-Kalai conjecture. So to tie things even more closely, what I will tell you now is an even stronger version of this question, and that will now be a common strengthening of the Kahn-Kalai conjecture and this general conjecture in the general setup that I state here. So, okay, so I proved this just earlier this year, and I will call this sharp selector process conjecture. So I'll write it and again explain to you. So always the setup is the same. And again, these weights are given to us. Then the conclusion is that with reasonable probability, you make it anything you want, let's say 1/2. You have that the maximum over H of the fraction of weights that you can collect. Okay, so this will now be changing a little bit. Instead of XP, what I will put here is X, well, constant times P times log 1 over epsilon. And what we get on the guarantee for the amount of weight that you can catch in the random set will be 1 minus epsilon. Okay, so, right, the only thing that has changed is that we did boost the sampling probability here up a little bit from P. We boosted by a factor of log 1 over epsilon. And as a consequence, what we can guarantee on the boost of the amount of weight that we can catch, which is anyway cannot be larger than 1, is that we can get up to a 1 minus epsilon fraction of the total weight. Okay. So let me first tell you that this is a strengthening of the Kahn-Kalai conjecture. So again, we just take the simple setup where we just take the weights to be uniformly distributed across the elements in the set H. And if we just take epsilon to be something like 1 over 2H, then you can say 2L, where L is the upper bound on the side of H. Then immediately what you get here is that with probability at least 1/2, you can guarantee that you can find some set H in the family script H, for which the fraction of elements that you can capture from that set H is at least 1 minus 1 over 2L. And the only way that you can do that anyway is to already capture the entire set H. So this guarantees that there exists with probability 1/2, there exists H such that X intersected So here is xcp log 1 over epsilon intersected with h is at least 1 minus 1 over 2h. Well, I guess times the size of h. 1 minus 1 over 2l times the size of h. And this is even bigger than h minus 1. So your only option is that already you contain h.
Here the H will be a monotone property or it does not be.
So h is arbitrary. So here we don't assume h is a monotone property, but implicitly we are only talking about the property of containing at least one set from h, which is automatically monotone. Okay, so that's one strengthening. And particularly for one of the questions that Hong asked actually offline, we see here that we see quite clearly, if you don't want to catch entirely the set H, but you want to catch up to a 1 minus epsilon fraction of it, then you don't need to blow everything up by a factor of log L. You only need to blow things up by a factor of log 1 over epsilon, which is a constant when epsilon is constant. So the last comment is this trade-off between epsilon and log 1 over epsilon is optimal.
In many cases, one can do like different round of random patches to boost its constancy. So
Right.
my guess is this theorem does not follow vanillally from.
No, right. So, yeah, so the proof of this theorem is already somewhat involved. And it happens that if you look very carefully at the proof, then it crucially forgets some information at various places, which will kind of make it impossible to run it even in a few iterations. So we can't directly improve the constancy by just iterating the proof that we know, or the result, or even the proof that we know here. So this proof is actually quite a lot more involved. And the proof of both of these turns out are quite a lot more involved than the proof of the Kahn-Kalai conjecture. So I will not at least tell you in full, but if I have some time tomorrow, then I will tell you at least some flavors and some of the ingredients that you may need to prove these results. And I will also tell you more applications that have a combinatorial flavor of this result tomorrow, if we have some time for that. But just as a remark, we will now go to the proof of the Kahn-Kalai conjecture, which was actually itself motivated by the proof of this question right here. So the original proof of this version without a sharp dependence. And it just turns out that the rich picture that's given to you by this general setup of Talagrand's conjecture, and in particular, the challenge in dealing with these general weights, it motivates us, it kind of forces us to discover the correct idea that in the end is fairly simple, that is the key idea in all of these results together with the proof of the Kahn-Kalai conjecture. And first I will tell you about that idea and the complete proof of the Kahn-Kalai conjecture. And if we have time, we will discuss a bit of what we need to approach these more general versions. Okay. And yeah, also, yeah, just kind of an interesting case where looking at something more challenging can actually give us insights to resolve the other questions. But after this, I will also return to kind of the more combinatorial, the original viewpoint towards the Kahn-Kalai conjecture or thresholds, and I'll discuss applications or connections to sunflowers, and you will see that that somehow right, this more general abstract picture, even though it's conceptually harder to work with, it gives us somehow more room to look at the phenomena and to understand things in the right way. But anyway, with that, let's now go to discuss the key idea for the proof of the Kahn-Kalai conjecture. So maybe I should first start by restating the conjecture or the theorem that we will prove now. So we are given a family of sets H. The assumption is that it is not peaceful. And now we sample a random subset of X with density CP and also is L bounded. So the maximum size of a set in A is equal to L. And we sample a set of density CP log L. And we want to say that it contains some set from this family with probability at least 1/2. So turns out that the key lemma, which I will state now and prove first, towards this result, has a flavor that looks somewhat close to this simple corollary here. So what's the key lemma? Maybe I should first set up some key definition first. Yeah, let me do it that way, might be cleaner. So first, key definition. In fact, the object is quite simple. So for subset W of X and some set H from the family strip H, let me define the following set. Let's back T, which is a set that depends on W and H, to be the minimum in terms of size, and you can factorize arbitrarily. Subset of H such that W union with T lies in bracket H. In other words, W union T contains at least some potentially different set H prime from the family strip H. In picture, you have W, you have your set H, and you are finding just the smallest amount of elements from H that you need to include into W in order to guarantee that W, together with these small sets of element T, contains some different set H prime from the family strip H. So to anticipate, if we discuss the ideas towards these later, I can also state this simple definition in a slightly different language. So if I let Z, which will also be an important object in our proof today. So we'll let be this union of W and T. So if Z is equal to W union with T of W and H, then it will have the following property. So we can, instead of defining T this way, we can first choose, so let's say that Z is feasible if it satisfies a simple condition of being in bracket H. We'll see why we go through a little bit more trouble here, at least conceptually later, when we discuss the proof of the harder results. And we choose Z, WH as the minimum, again, in terms of size, feasible subset of W union T, W union H. Okay, and if you choose Z first this way, then you can just define T to be Z minus W. Okay. Regardless, you can just think about maybe the original way in which we define this set T of W and H. We'll call T a minimum fragment for what it looks like. So T, smallest number of things from H we need in order to make the union of W and that small set something that is feasible, that contains at least one set from the desired family. Now I can state the main lemma. The key lemma says that, well, for every W, a subset of X, we can first fix W and allow W to interact with every set from the family H. So when W interacts with each set H, it produces one fragment, T of WH. Let me this is a collection of sets depending on W, be the collection of all of the fragments TWH, where H is some set from our family script H, W is fixed, and the size of T is at least L over 2. Remember that L is the upper bound on the size of the set H from our original family. Okay, so for each fixed W, we go over all H, and we look at the H for which the fragment T that they produce with W is required to be quite large, is at least half of its size. And then we just put all of these large fragments into this collection UW. So our claim is that the expected value, so now we take W to be a random set, and then we average over the distribution of this W. W will be a random subset of X, where each element is chosen with probability C times P. And then we will look at the cost of this family. In other words, this is just the sum over all the sets U in this family, P to the side of U. And the claim is that this is fairly small. So think about C as a decently big constant. This is the main lemma. Any question about this main lemma? Maybe if not, I will tell you first, okay, roughly how to use it to derive the full conjecture, and then we will prove the key lemma. And then we'll also see later that the proof will just the same proof. Once we are familiarized with it, we can use it to prove many other different corollaries in slightly in different contexts. So hopefully we can introduce it in a way that everyone can get familiarized with it. Okay, so maybe first just about how to get the conjecture from this key lemma. And given what is stated in this key lemma here, what you need to do will now just be essentially an iteration. Okay, so let's set up the iteration. We will sample different independent, different sets with that same distribution XCP. So let's sample W1, W2, according to this distribution X, C times B. They're all independent. And in the end, the number of sets we will sample will be roughly some constant log L. Okay. Now, we will also define correspondingly a sequence of hypergraphs, a sequence of set systems. Also, we'll define H, which is equal, to H naught, which is the set system that we start with in this iteration. And then this will evolve according to how the set systems interact with this random set W. And at the same time, as we see over there, whenever the set system interacts with W, it produces this collection UW, which we will also keep track of. Okay. Okay, so that is a little bit formal, but what will happen in the end will be simple. So we started first with our family H naught, and then we have our first sample W1. Okay. Now there are two different types of sets in H naught. There are those that produce a small fragment, and there are those that produce a large fragment, where large means bigger than L over 2, and small means smaller than L over 2. Okay, well, I will define U1 to be just exactly the family of all of the large fragments. So exactly the family that appears in the key lemma. Okay. And then all of these sets, yellow sets, we'll take them to be the next set system that we use in the iteration. So these will be H1. So what property do we have? Well, the union of W1 and any set in H1, we are guaranteed by how we define the fragment that they will contain some other set from the original family H. Right? So we are guaranteed that together with W1, outside of from each of the sets in H1, we can complete a set that belongs to the original family strip H. In particular, in the future iteration, instead of trying to make the union of the W containing some set from the original family H, I can just focus on forcing the union of W2 to WC log L to contain at least one of the sets from the family H1. And that together with W1 would be enough for the union of all of these to contain one of the sets from the original family. Okay, so just rewrite the guarantee here in this simple first iteration. So if W2 union with WC log L contains some of this yellow fragment in H1, then the union of W1 and all of them will contain some set H prime in the original family H by the definition of the fragment. Okay. Of course, the other nice property that we gain is that the uniformity, the size of the sets in H1 have already decreased by a factor of 2. Okay. We do lose a little bit. So not all of the sets in H0 kind of give rise to a set in H1. There are some of these bad guys. But the key lemma tells us that all of these bad sets in H0, which do not give rise to a small fragment, anyway, they can be covered by this collection U1, which have in expected value a very small cost. Okay, so this is how we will do it. So we will guarantee, as we run the iteration, that okay, so well, maybe I should formally define the iterations in the later steps just to keep it clear. Okay, so in every step, what we will do is we look at the collection Ui plus 1. This is exactly the collection of all fragments T Wi plus 1 Hi, where Hi belongs to Hi, and T is a bit too large. Okay, so I don't get off by 1, but I may get off by 1 at some point. Anyway, so as we see in, of course, in this iteration, the uniformity, the size of the sets in the family Hi, we will just guarantee that they are shrinking by at least a factor of 2 in every step. So if we started with L, then in the ith iteration, we'll get L times 2 to the minus I. And so the large fragments, which we will pull into Ui plus 1, are exactly those that have size still below this L times 2 to the minus I plus 1. Okay, then we define Hi plus 1 to be exactly the set of all of the fragments such that its size is small, is below the threshold that we want. Okay, and the property we will observe is that every set in, let's say, our original family of sets H with no subset in Hi, it must be covered by the union of these leftover collections U's that we have put aside. Okay, so it can first check this in the first iteration and can kind of see that if you just run the iterations longer, then this property will always be guaranteed. So for every set in H, it will either have an offspring like this that survives to the next round, or if it dies, it means it must produce a large fragment in that round. So if it produces a large fragment, it will automatically be covered by one of these collections U, in particular the collection U at the time where the set dies, and that collection U, so U is a collection of sets that produces a large fragment, and it by the definition it will automatically guarantee its property. Okay, and just similar to the observation here, you will have the property that for any set H from the family Hi, the union of W1, W2 up to W and I union H will have to be long.
To be precise, should we say there is, in the first bullet point, should we say if it's not already covered by union of so far Wj's, because it could be empty. Do you include empty set in Hi?
Yeah, I will allow empty set to be in
Okay.
Hi.
Okay. Yes.
Right. And we'll see that in a second. So for now, we are allowing empty sets to be in this collection. But when empty set appears, it's good to install it. Right. So yeah, the other property which just corresponds to this claim that we had before here in the first iteration is that any of these HI, they do have the property that together with the union of the previous random sets, all of them would form some set that lies in this desired collection, bracket H.
I'm confused with the definition of two I. So is it just the union of the subset of some H, or just for each, or it is just union of the for H, which is not covered by this HI?
Oh, no, so the U's will just be the collection of these red sets.
Breadth.
Yeah, so not H, right? So it's the sets of a set of fragments T for which the size of that fragment is large. So we're just taking these large sets and put it in this collection U. It could be the case that there are multiple sets in H that give rise to the same fragments, so the same red set, in which case we'll only include the red set ones. Yeah. Okay. So of course, the last property, which is simplest to guarantee in this iteration, is that the size of HI is at most L2 to the minus I for all sets HI in this collection HI. So if you have chosen your constant here big enough in front of log L, then of course every set in HC log L have size less than 1. You can guarantee that. In particular, this is a collection of sets that's either the empty collection or it's the collection that just contains the empty set. Okay, so what are the two things that can happen here? Well, if this collection HC log L contains the empty set, then by this property here, so this together with this, they imply that the union W1 up to WC log L, this belongs to bracket H. Okay, and this is good for us. So this is kind of actually it's dominated above by just a random subset of X with density C times P times C log L. Maybe a bit clumsy, but just ignore the constant. This is a random set with density some constant times P log L. Exactly what we want. And here it falls into the collection that we desire. So there's the other case where the collection HC log L is the empty collection. Well, if it's the empty collection, then of course every set in H cannot have a subset in that collection. So in this case, the collection U must form a cover for the collection H. Okay, so we have one of two cases that kind of okay, so this is a case that we want. This is a case that doesn't imply what we want. But in this case, roughly, the key lemma tells us that we have a small cover for H, which is not possible. Well, of course, not exactly that because we only get small unexpected value, but that's exactly how we are going to finish the argument. Okay, so, argument. So, by the key lemma, the expected value of the cost of these collections used over the randomness of the sets W. They are all distributed like XCP. This is at most, well, twice 4 over C. And then you have this kind of telescoping sum. You have this sum here. To the minus I. Of course, you can always assume that Ly is at least 1. If Ly is already 0, we don't have to do anything. So we should only sum this when we sum this over I, but the Ly is decreasing geometrically, and then we stop the summation when Ly hits 1. Okay, so anyway, you can be a lot more careful with the process to kind of boost the density of the random sets closer to the end and so on and so forth. You can do some tricks here. But if you just use the vanilla version and you choose C to be large enough, then we can easily guarantee that this sum is going to be small, any small constant that you want. Okay, so in particular, let's say smaller than 1 over 8. By picking C large enough. Then, okay. The probability that this cost here is big by Markov inequality. This is at most a quarter. But we know that whenever H is covered by this collection, we must have that the cost of the collection is at least 1/2. So in particular, the probability that this union covers H is at most a quarter. So this red event has at most a quarter chance of happening, and in particular, with probability at least 3/4, the union of the random sets have to lie in H. Okay, so this is what we want. Of course, you can write this in other ways, and you can optimize the parameters if you're interested in the constants, but roughly all that happens is this iteration here. And the key input is really the key lemma. So, okay, it's good point. Maybe I'll take questions and we can take a 5-minute break. Any other question before we now prove the key lemma? Okay, so this proof should be the most important one for today and tomorrow. So we'll see, hopefully again, many different variants of this proof once we are comfortable with it. Okay, so I'll exchange something from the probabilistic language to the combinatorial language just to make it a little bit more intuitive in a bit. So for that, let me define one small piece of notation. So let me denote this probability under probability CP of a set X. Well, this is nothing but the probability that the random subset XCP is equal to the set X. So this is nothing but, of course, CP to the square X, 1 minus CP to, I shouldn't use X. Y, X minus X. Okay, so notation. So really the key lemma, we'll do a small sequence of calculations in a little bit, but again, it all relies on the following very simple key property. What's the key property? So if we look at a set W. Okay, so what did we have from the definition over there? The key definition. We're given a set W in X and a set H from H. And we produce this fragment T of WH. And then we produce this set Z, which also depends on W and H implicitly, which is a union of W and its fragment with H. Okay, so in the picture, I have a W with H, and then we define this fragment T, from which we get also this set Z. Okay, what is the key property going to say? It's going to say that in some sense, well, in this picture, if we temporarily forget about what happens out here, we'll just focus on what happens inside this red zone. So inside the set Z, in this picture, we are given the set W and the set T whose union is Z. So in other words, we are given this information of the boundary line between W and T. The key property tells us that if we have chosen T to be a minimum fragment, then it somehow is very structured, so we can easily identify it. And at least what we can do is we can identify T inside Z without paying a lot of cost. So, okay, let me write it, and then we'll see how we will use it. So in the set Z, so now I just give you this red set Z with no information about where W, H, and T are. Okay, so we forget everything in this picture apart from the set Z. No matter, okay, so for every set H prime from the collection H star, from the collection H, such that H star is a subset of Z, we have the property that T sits entirely inside H star. So in other words, that gives you one way to recover at least the W and T part of this picture, only given the knowledge of Z. What you do is you pick an arbitrary set H star in Z that comes from the collection H. And in H star, you specify T as a subset of it.
Is this T is with respect to this H star and W?
No, so
Just
T was with respect to W and H. Right, and now we certainly don't know what W and H are, but we are given Z, and still we can say that this T of W and H sits inside H star. Okay, so to justify this is extremely simple, right? So if there exists an H star in there where T is not a subset of H star, then, well, I can, okay, so then what does that look like? So does that T somehow have some elements outside of H star? Oh, but then if I just define a new set, T prime, which is the intersection of T and H star, so this smaller subset, we can still guarantee that W together with T prime contains at least one set from H, in particular the set H star. So this now T prime is a strict subset of T, that still satisfy the property that we want T to be minimal with. And in particular, that contradicts the minimality of T. So very simple. Question about this P property. Okay. So in a formal sense, what we will be able to do with it is kind of this following very simple injection or change of variables that we will very soon see. So we will very soon see that the key lemma is really about controlling the pairs of sets W and T with the following property, with the property that you expect. So with the property that T can be written in the form TWH for some H from H, and maybe the size of T is a bit too large. Yes. And through the key property, we have an injection of this into the following collection of sets. So what we do is we kind of change our perspective. Instead of counting the pair W and T, we will count first from the set Z, and then identifying T as a subset of H star in Z. Then W will just be defined as Z minus T. Okay, so that's what will happen. But again, before that, let me set up one important step. So for every feasible Z, so every Z in H, let's fix in advance an arbitrary choice. H hat, which implicitly only depends on the set Z, which is a set in H that is a subset of Z. And of course, we can do this upfront for every set Z that has at least one set in H inside it. Okay, so given this notation, the injection goes like this. So we will map W, the pair WT, to the pair Z minus T and T, where, well, Z is a feasible set. Okay, anyway, the union of W and T here would always be feasible by definition. And T is a subset of H hat Z of size at least L over 2. Okay, so the claim is that the key property is just roughly translating to this injection. If you count over here on the right, you will encounter every possible pairs that you may see on the left. Key property. Okay, so with that already set up in that exact way, I will now finish the proof of the key lemma. It will just be a couple of so for the key lemma, what do we need to prove? We need to prove that the expected value over W, sample according to XCP, of this quantity is small. Let me rewrite it this way. I'm just going to sum over all subsets W of X, well, it's sampled from this distribution. So let's put its probability here. Okay, now what do we sum inside? Well, we sum over the sets in the collection UW. That's just the collection of the big fragments T to the size of that fragment. So I will just sum here. All of the sets T of size larger than L over 2. Okay, maybe let me write this way. P to the size of T, indicator that T is a fragment of W and H for some H. Okay, so just rewriting the definition of the collection UW. So if you want, you can rewrite this now as the sum over pairs W and T from exactly that collection here. And what you sum inside is PCP to W, P to the size of T. Okay, now I have a sum on the left. I want to use this injection to bound it by a sum on the right. So this is less than or equal to. Now instead of summing over W, I'm summing over Z. The constraint is that it has to be feasible. And instead of T, well, here what is T? T is a potentially arbitrary subset of H hat of C of size at least L over 2. So let's put that here. T is inside H hat of C of size at least L over 2. Okay, we have not changed what's inside here yet. So PCP of W, P to the T. Okay, well, let's do one small piece of gymnastics here. So PCP of W is, well, we know before, it's nothing but CP to the size of W, 1 minus CP to the size of X minus the size of W. Well, what's the size of Z? If I let T be equals to the size of T, right, then the size of Z is exactly the size of W plus T. So you can check that if you look at PCP of Z, which makes more sense to put here than PCP of W, which is why we are doing this, then this is PCP of W multiplied by 1 minus CP to the T over CP to the T. Okay, so let me plug this in here. Wait, actually, swap the order. One step too fast. CP to the T over 1 minus CP. So if I plug that back in here, then this is the sum over all of the same constraints. But now we have P to the size of T, 1 minus CP to the T, CP to the T. Okay, we already see some nice cancellations. Right there. So let's quickly finish from there. There was a question. Oh, sorry. Yes, thank you. Thank you. Yeah, we need PCP of Z. Okay, so, right. So let's now rewrite exactly that last expression that we have this way. So let's first sum over Z. We have this constraint, won't be so important. We have this probability let the set Z appear. So very nicely playing with this sum. And then we have the sum over T, right? So T subset of, okay, so let me now write it a bit further. So the sum over all T bigger than L over 2 at most L, say. And then I sum over T subset of H hat of Z of size exactly equal to T. And if I sum like this, then the quantity in there is what? P to the T, Cp to the T, 1 minus Cp to the T. Okay. This is canceling, so you get C to the minus T. And this is anyway at most 1. So we can erase that. Okay. Now, this guy is easy to control, right? Well, H hat have size L and T have size T. The number of choices for this set T is going to be at most L choose T. So we just have the sum over Z now. PCP of Z. The sum over T bigger than L over 2. C to the minus T, L choose T. This sum here, the numerical sum. And you can easily see that, well, L choose T anyway is at most 2T choose T, which is at most 4 to the T. So you get 4 over C to the T, and T is at least L over 2. So it's some elementary estimate to bound this by kind of what we claimed before. And this sum here, this is a probability distribution, so I have to sum to it also.
Is essentially type or there's is
So, oh, right, a good question. So this in the general setup, it's not clear what one can use to improve it. I don't know if I can say that it's type. We'll see that in a lot of the applications that I will get to tomorrow. And what happens is that we have some additional knowledge, there are some additional constraints in the problem. And what will happen is that then we can always just improve this part. So this is kind of the key in the working, and in every application, this is kind of the only calculation that we are modifying. But generically, maybe there's not, yeah, I don't know how we can find an improvement here. But if you want to get, the correct constants for everything, then you have to choose things carefully. You shouldn't. There's this choice that I make somewhat arbitrary here, where I declare large means L over 2. You have to tune that carefully and do the estimates more carefully. But
Cost being small means they are unlikely to be many of them. Is that- So this lemma is saying, although there could be some large fragments, but they are in the expectation probably not so many.
yeah, so somehow the translation between being small in the language of cover and the count, it's not quite, doesn't quite work, at least directly. So this, yeah, doesn't, in a sense, it does translate to the fact that there cannot be so many, well, actually, so there cannot be so many large fragments. That's roughly the equivalence of what we are proving. If you want to translate it back to something like there cannot be many sets in H which are sitting on top of the fragments, then that is a bit more questionable somehow. Under just the conditions that we are assuming right now, we can't directly make that deduction. We'll see tomorrow other setups where that deduction will be natural. So we'll revisit that. But here, indeed, roughly what we are proving is that there cannot be many large fragments.
The fractional Kahn-Kalai where they have this additional pseudo randomness, you don't even have any large fragments, right?
That's right. So yeah, we'll get there tomorrow. So we'll see very directly. This will give you a very streamlined and quick proof to see that if you assume that stronger condition, which I haven't told everyone yet, in that H is not fractionally P small, it's stronger than H is not P small, then you can deduce that most sets from the family H can only produce a small fragment. So in that sense, indeed, you can prove that the number of sets at least sitting on top of the large fragment is a small fraction of the collection H. That conclusion is not true, so we cannot deduce a similar conclusion only under the assumption of being not true.
Are there any universal criteria to check whether H is not P3?
Right, that's a good question. So, right, so H being not P small is the same as putting an upper bound of P on the expectation threshold. And tomorrow, I will tell you, as Hong also just suggested, there is a fractional relaxation of the expectation threshold, which is a general way to put an upper bound on the expectation threshold. And at least for many of the combinatorial questions that we will see, many of the nice simple applications, that is the way that we can verify that H is not P.
So there's a question in the chat asking for fixed W and H, is the fragment TWH unique?
Yes, so as I said, it is not it is unique by choice. So fixed W and H, there could be many sets with the same minimum size that satisfy the property that the union of W and T is in bracket H. You can just break the ties arbitrarily and make any one of these choices. So in general, it's not unique, but you can just choose one. And whatever rule you use to choose one, you can think that T is chosen uniquely according to something.